In this video, we're going to discuss the Central Limit Theorem. The Central Limit Theorem is one of the most important concepts in statistics, and it says the following. For a population with any distribution, the distribution of the sample means from that population approaches a normal distribution as the sample size increases. Further, if the original distribution has a mean of mu and a standard deviation of sigma, then the sample means from samples of size n will be normally distributed with a mean of mu, so the same mean as above, and a standard deviation of sigma over the square root of n, the original standard deviation over the square root of the sample size. Sometimes this is written as sigma sub x bar because it's the standard deviation of the sample means of size n. The central limit theorem works, or, we say that the central limit theorem applies in a situation where sample sizes are reasonably large or the original population is normally distributed. So as long as at least one of those two criteria are satisfied, the central limit theorem works. What do we mean by reasonably large? A lot of people use n equals 30. In other words, the samples that we take the averages of are at least size 30. Some other people use n equals 25, and either of those criteria are acceptable. So that's like a lot to think about. Let's think about a particular example. Suppose that you're tossing a six-sided die. We know that the values of die throws have a uniform distribution because each value is equally likely. So, a 1, 2, 3, 4, 5, and 6 are equally likely, so we have a uniform distribution across those values. A uniform distribution from 1 to 6 has a mean of 3.5 and a standard deviation of 1.44. So suppose that you toss a die 30 times, and if you do that, you'll get a distribution that's close to the uniform distribution. So here's such a set of 30 randomly chosen numbers between 1 and 6. And we see that, this is not perfectly flat across the top. It's not perfectly uniform, but this is meant to model a set of actual data. So it's close to uniform, but not exactly. Then we can take the sample mean of this data. So, we've got the die rolled a 1 5 times. There were 5 1s. There were 6 2s, and so on. So we can find the sample mean for this. It's each data value times the frequency of that data value divided by the number of data values divided by 30. And if we do that, then we'll get a sample mean of 3.43 for this set of 30 data values between 1 and 6. And so this is a sample of n equals 30 die throws. We take the mean of the sample as we did above. We see that the sample mean is 3.43 for this particular set of data. So if we do this repeatedly, we do another set of 30 die throws and take its mean, and another set of 30 die throws and take its mean, and we graph those. So here's maybe our 3.43, and we do it again, and we get 4.1, and we do it again, and we get 2.97, and so on. We plot the sample means that we get. So we roll the die 30 times, we take the average, and then we plot this average. Then those sample means will get pretty close to a normal distribution. It might not be absolutely perfect, but it will be close. So these are sample means, sample size, n equals 30 each. So each of them has sample size n equals 30, and there are 20 samples, 20 sample means here, 20 sample means graphed. Now, what the central limit theorem says, again, is that those sample means will be normally distributed or approximately normally distributed, and that it will have a mean of the original mean. So the original mean for this distribution was 3.5, and the standard deviation for this distribution of the sample means will be the old standard deviation divided by the square root of the sample size. So in our case, that was 1.44 was the standard deviation for us divided by the square root of 30. That means the standard deviation for this set of data should be approximately 0.263. So a much smaller standard deviation than we had above. In other words, this data is packed way more tightly together than this data. This data is more spread out. And this data is packed more tightly together because it has a smaller standard deviation than the original set of data. If we used sample size n equals 100, and we took sample means, and again, so we rolled the die 100 times, we took the average of those 100 rolls, and we did that 20 times, and maybe one of the times we get 3.56, and another time we get 3.43, and so on. But these sample means are going to be closer to the original mean. The original mean, 3.5, is going to be the same as the mean for this distribution. And the standard deviation for this distribution of sample means now is going to be the old standard deviation divided by the square root of the sample size. So that's 1.44 divided by the square root of 100. So that's 0.144 is our new standard deviation. It's smaller still than what we had before. And that means that these sample means are going to be even less spread out than what we had before. So this is still going to be a normal distribution, but it's going to be taller and skinnier than the normal distribution that we had above. So the larger the sample sizes are, the more closely the sample means are packed together. The central limit theorem is incredibly powerful for applications such as hypothesis testing. So, for example, let's say the length of pregnancies are normally distributed for humans with a mean of 268 days and a standard deviation of 15 days. Suppose a particular diet has become popular, and researchers want to know if this has any effect on the length of pregnancies. So they track the pregnancy lengths of 64 women on their diet and find that the average pregnancy length for these 64 women is 263 days. So let's think about this. First of all, let's observe that the event that just one woman has a pregnancy length of 263 days or less is not particularly unlikely. So, 263 days or less. Over here we have graphed just this normal distribution sketched with a mean of 268, a standard deviation of 15 days. And so if we look at, where does 263 days lie? 263 days like here, we can just sort of see visually that that's not going to be particularly unlikely. To get a precise value, we could do a z-score. So the z-score for this is 263, our data value, minus 268, our mean, divided by the standard deviation of 15. And so we would get a z-score of negative 0.33. And if we look at either a table or a computational device and find the probability that z is less than negative 0.33, we'll find that that's a probability of 0.3707. So 0.3707. So basically a 37% chance that an individual person's pregnancy is 263 days or less. Not especially unlikely, more than a third of the time. But the probability that a sample of 64 women have an average pregnancy length of 263 days or less is very low. So by the central limit theorem, now these sample means will have a normal distribution with the same mean as the previous, 268. But now the new standard deviation is the old of the sample means is the old standard deviation, 15, divided by the square root of the sample size, divided by square root of 64. And so the standard deviation for these sample means is 1.875, so much smaller. So here's that normal distribution, the approximate standard deviation, one up and one down, is shown. And so now we're looking at a pregnancy length of 263 days or less on average for this group of 64 women. And this probability, as we can see visually, will be much smaller. To be precise about that, so if we did a z-score, then that's the data value. This is really a sample mean minus the mean for the distribution divided by the standard deviation for these sample means. Now that is, our sample mean that we're interested in is 263 minus the mean for the distribution, 268, divided by the standard deviation of these sample means, and if which we found was 1.875. So when we find that z-score is negative 2.67, almost 3 standard deviations below the mean, as we see over here. And if we look at either a z-score table or a computational device, the probability that z is less than negative 2.67 is 0.0038. So that's much smaller. That is less than 1%. That's less than 0.5%. That's very small, and that's statistically significant because it's less than 0.05. So if this result was found, that is saying that if there's nothing unusual about this group of women, then the probability that the average of their pregnancy lengths is 263 days or less is 0.0038, less than 0.5%. Therefore, a result this extreme is probably because of the aspect that is separating these women from other women, or the thing that is special about them, which in this case is their diet. So this is evidence to say that this particular diet, whatever it is, paleo, vegan, whatever, is cause for concern because it decreases the length of pregnancy, and shorter pregnancy lengths are correlated with negative outcomes for newborns. So this would be an important research result. So because the central limit theorem shows that the standard deviation of the sample means decreases, that these sample means will be clustered much more closely together as the sample size increases, this allows us to get more statistically significant results. So, if you were just talking about for one individual woman, it would be really hard to get a statistically significant result. You'd have to be, more than 2 standard deviations below the mean, a pregnancy length of fewer than, 238 days, and it just wouldn't be, it would be hard to get that statistical significance. Versus if you're talking about a sample of size 64 or a sample that's larger, small differences in the sample average correlate with very highly statistically unlikely outcomes, or statistically significant outcomes. One last comment is that the central limit theorem does not say that large sample sizes are always normally distributed. Like, for example, die throws, those will never be normally distributed just themselves. They will always be uniformly distributed. Even if we threw a die, 1,000,000 times, that would have a uniform distribution. It's sample means from that distribution that are normally distributed according to the central limit theorem. So sample means or sample averages are normally distributed according to the central limit theorem, no matter where they originally came from, no matter what kind of distribution the original data set came from.